So, welcome to the Machine Learning Fundamentals seminar. I guess it's going to be a quick little dive into some basics of machine learning. It's not going to go super in depth. There's a lot of stuff I wanted to try to go through. So I may not get to everything promised. So apologies in advance for that. That said, who am I? So my name's Tyler. I'm an electrical engineer. I've worked in a variety of industries, starting off in nuclear, where Tom and I met actually, and moved into some aerospace engineering for a little while, doing some robotics work, which did involve a little bit of the machine learning type stuff. That got me interested in automation systems. And eventually the siren song of cybersecurity called, and I went into SOC analyst work. Got some good experience doing some analytics there. Big data has always been interesting, and being able to traverse it quickly is really cool. So got into penetration testing, doing consulting side work for an MSSP, and then eventually landed where I'm currently the purple team person for a consumer electronics company. So I've had a variety of random things. So why are we giving a talk about machine learning in a cybersecurity convention? So a lot of people come to VetSec and they are very interested in LLMs, large language models. They are like, oh, ChatGPT is really cool. I want to learn about that. And we often also, as cyber professionals, see that people are being sold these AI, ML, LLM, whatever type products. And honestly, I'll often kind of talk to the sales folks, and often they really don't know what it is they're selling. And in a lot of cases, hooking something up to ChatGPT is really not the best use of anybody's time. It might be, computationally expensive, actually expensive from licensing costs, and it might be that a traditional machine learning algorithm is a better fit. And that said, even with machine learning, there are many cases where you don't actually need machine learning. You just need regular statistics. So, kind of wanted to talk about what some of the stuff actually is, how it works under the hood. And then also, since we do have a lot of students or prospective students joining VetSec, LinkedIn, or random Discord channels that I'm in saying, what is AI? They kind of want to understand how it works on a foundational level. And there's a lot of steps that go from your basic like symbolic logic all the way up to large language models. But I'm going to try to kind of explain some of the intermediary steps to at least get people on the right course to kind of understand where to start looking if they want to go into AI or ML. So got some agenda for you, fancy and cool. So we're going to go over some basic terminology first. So whenever we look at machine learning models, we have two major categories of things fall into, categorical and numerical. So categorical is where I want to predict the label that a system will produce as an output. So that might mean that I want to try to say, what type of dog breed is this based off of some input data, like its height, weight, muzzle length, tail length, etc. I can often find common input parameters and label things based off of known values. Computer vision. So we know what a dog looks like. We know what a cat looks like. How are they different? And how can I make an algorithm understand that? And then since we're all cybersecurity professionals, we do like to categorize things based off of risk. We like to attribute things to different threat actors. We like to understand what category of MITRE attack map might go to, or something of that nature. Now, numerical prediction, that's much more in your classical statistics modeling. Any type of regression analysis, we're doing linear analysis, using equations to solve a numeric problem. So maybe we want to predict a number where that number could be a certain set of values. And that can either be like an exact number or maybe a range of numbers. So big thing, categories and numbers, continuous or discrete items versus continuous items. So with learning, there are a couple different ways we can do our learning. There's unsupervised, supervised, and reinforcement. And we're going to mainly talk about unsupervised and supervised in this lecture. Reinforcement is a bit more advanced, so we won't go into that very much. But unsupervised is where we don't really know what our output's going to be. We give it a set of known inputs, and we do not necessarily know what the outputs are going to be. So that's a little confusing, but what it really means is that I cluster some things together and I find some common labels in that group. So maybe I have a collection of data about a dog, and I can predict maybe the breed, maybe the height, maybe the weight. I don't necessarily know those going in, but I can kind of categorize them coming out. Maybe I don't necessarily know which advanced persistent threat is conducting a thread operation, but I can try to say, well, I have 10 of these guys, 20 of these guys. I'm going to cluster these guys together, and now I have a common label to use going forward. I didn't know that going in whenever I looked at the data initially, but after analyzing the data, I know what my commonalities are coming out. Supervised learning is a lot easier. I know what I want, and I build the model with that known output feature. So I say, here are my input features, here are my output features. Give me the best model that gives me the most accurate output feature recognition. So maybe I want to try to predict what occupation people are whenever they're flying. I can take in their age, destination, I can take in where they're coming from, where they're going to, how much baggage they have, any amount of information about them. And then I can try to take a sampling of the known occupations, and I can try to create a model that will accurately predict based off of all those input parameters. And all of those input parameters are not going to actually be useful. Part of what machine learning model training is recognizing which of these input parameters are actually useful and which ones have either a positive, negative, or no correlation to the output. So again, to kind of restate that, because that's a really important aspect, it's understanding which input parameters have a positive or negative correlation, because if it has a negative correlation, it can still be useful in finding an output. But if it has no correlation, it's just not useful. It's just noise. So we can discard that. And some of the stuff we're going to talk about later, some of the things we do is trying to find those input data that are good to reject. Reinforcement learning. So that is getting into the more advanced things. So with that, we're trying to take a model and then improve that model based on the previous output of that model. So you have multiple stages, you have rewards, and you say, okay, I classified this correctly. I used these weights. Let's increase this weight and see if I classify more things correctly based on this output. And that's where you start getting into more advanced things like neural networks and things like that, where you have multiple or numerous stages and you're trying to build something based off of the prior inputs. And also the reinforcement learning, it can either be computer driven or human driven also. So you can have humans sitting there clicking, yes, this is correct, no, this is incorrect. And that's a little bit of what the CAPTCHA stuff we do is doing. You know, we're actually training models for Google and whatnot. So we have two major terms for understanding how our models can be wrong. That is bias and variance. Now, prediction error is what's happening whenever our model is fitting too tightly. That means that the model is too specific and small outliers can drive the model excessively. Bias is where we just don't have an accurate enough model. So we always have to kind of balance those two aspects. So we kind of talked about some of the things we're looking for, some of the different classifications. Ultimately, all of our machine learning models are going to be built based off of collecting data, be it continuous or discrete, numerical, categorical, whatever. We're going to fit the data, and that requires us to put the data into the model and then put certain parameters around it. And we're going to adjust those parameters to try to get output that evaluates correctly. Now, we can either overfit a model or underfit a model. We can have too much loss. We can have all sorts of different things that go wrong. And that's where we train the model to try to get rid of all that. So I'm going to talk about some classification models. Here is k-nearest neighbors, one of the more common ones we're going to see. KNN, k-nearest neighbors. So that's where we are taking some data points, we are putting them up, and we are trying to find them that are close physically together to each other in order to cluster them together. So what is the K? The K is simply the number of neighbors that we're going to consider whenever we're trying to think of what something actually is. So if we look at the green section, for example, there we got 4 circles and 1 diamond. So if I look at that very top circle there, then I'm going to see pretty much no matter what I put in, my nearest neighbors are always going to be circles. Unless I like get, 20 of my nearest neighbors, then it's going to tend to be a little confusing. But as long as I pick, 1 neighbor, 2 neighbor, 3 neighbor, 4 neighbors to consider, I'm always going to have most of my stuff is going to be circles. Now, if I'm that diamond that's in the green there, though, it gets a little more confusing, because if I look at my very closest neighbor, I might say, well, maybe it's the star, maybe it's the circle. And you kind of have to tune it so that you are looking correctly at what something actually is. So we have to adjust our K values in order to kind of make sure that we're collecting all the outliers where they belong. And sometimes you just have to reject outliers completely. So some things you just can't fix. So we calculate distance in our KNN through a couple different ways depending on how the model ends up coming out. We can either pick like an absolute difference, that being like the orange coloring here of like maybe the Manhattan style, which is where you do it how many steps something is away, and you aren't allowed to like use geometric means or anything. We can use Euclidean style, which is where you're using like the Pythagorean theorem or something to get the absolute closest approach. Or you can use a complex generalization of these two put together and then calculus it out and do something that combines both. And really, different models react differently to different distance metrics. You kind of just have to experiment and train it and see which way works best. And this is kind of part of that tuning that I discussed earlier. So logistic regression. This is where we're trying to predict something based on input and output features, and we build a boundary. Now, we're going to talk about boundaries a lot more in this, but basically logistic regression is trying to come up with a boundary equation, this little linear guy here, and that says, hey, everything to the left of this is one thing, everything to the right of this is something else. Maybe it's above, below, whatever. This also works in multiple dimensions, so it might not be as easy as looking at a picture. We do have multiple linear logistic regression, which I have one here. Yeah, so we can also have a nonlinear boundary. This can cause very confusing looking pictures, such as the three-dimensional thing I have up above here. And these boundary terms can be planar, they can be geometric, they can be all sorts of different things. So logistic regression is trying to find some equation that correctly defines the boundary between my object classifications. We also can have threshold tuning. This is where we say, well, as long as it's, close enough to the boundary, we're going to give it a probability that it's one thing, a probability that it's another thing, and then let somebody decide, maybe a human, maybe the computer, whatever. So thresholding is also part of what we look for in logistic regression. A Gaussian naive Bayes, this sounds very fancy, and it starts getting really into where the probabilities come in. So I'm not going to delve into probability. That's kind of its own course on its own, but we look at probabilities of events. We can look at probabilities of other events, and then we can say, if this event happens, what is the probability of this event? So maybe if I have a blizzard, what is the probability that a concert is canceled? What if there is no blizzard? Is the concert, what's the probability that it's canceled? This is where you're looking at conditional probabilities. And there's a lot of math that you can do. It's not actually hard, it's just multiplication. It's called Bayes' rule. And this allows you to convert your conditional probabilities to individual probabilities based off of the other condition that you're looking at. So why is it naive? Well, because this all assumes that we're using independent variables. And in reality, these variables are not typically going to be actually independent. But we assume this just to kind of make a quick assumption to make our classifier work. Now, how does that look? Whenever we're doing this with real data, we have to bin the data into categories. And this can be numeric, it can be label-based. But if in this example right here, I've taken a normal distribution, just a Gaussian distribution, a standard bell curve, and I've said, okay, between each of these values, the -4 to -3, -3 to -2, each one of these we're going to consider a bin. What is the probability that something falls within that bin? And I'm just going to say that's the number of items in that specific range. I calculated out to give a basic conditional probability for that bin. So probably makes sense still. It gets a little more complicated, but we're going to go into that. Now, let's say that I'm trying to classify something based on conditional probabilities. In this case, I'm trying to figure out which dog I have based on who's a good doggy. So in this case, we've calculated conditional probabilities on a curve for each of my 3 dog breeds. And I know between each of these good doggy factors, which breed I'm going to get conditionally. So this might seem very simple, but this is really how it works, is that if I am in a range of specific bin values, i.e. the -5 to -2.5, I know that there is a very high conditional probability that I fall into the green bell curve here, which is a beagle. Now, all that your naive Gaussian classifier does is it looks at the conditional probabilities for everything that falls on a curve, and then says, what has the highest conditional probability out of all my selections? And then it goes with that. So the hard part, of course, is creating the data curves and understanding what all the conditional probabilities are going to be and actually selecting the right thing. And then it also assumes that everything's independent, which is not going to be. But that's basically how this classifier works off of conditional probabilities. So The last thing we're going to talk about for this category is discriminant analysis. This gets into the much more complicated mathematics. So it utilizes a covariance matrix to take relationships between multiple features, and every feature has a relationship between another feature, and then use linear algebra to try to figure out exactly what the strong relationships are, and then you plot logistic regression off of that calculation. It's more complicated. It's something just to talk about as a future study. Regression models. So linear regression, we've all actually learned this. This is just your basic y equals mx plus b. You are solving for a prediction based off of a simple slope. So if I have y equals x plus 1 and I want to solve for y, I plug in for x. It's very simple. Now, it gets more complicated because we can use multiple linear regression, which uses multiple variables. So it might be y equals mx plus dz plus b or something of that nature. Multiple linear regression gets a little more complicated. This is just projecting stuff based off of linear analysis. Elastic net regression, this is where things get a little more complicated, and we're trying to now start to calculate some tuning out. Now, with regularization, we're trying to optimize model parameters, and in doing so, we're changing the weights of our given slopes. So in that thing where I just talked about with y equals mx plus b, maybe I'm going to adjust the m value and get a slightly different result, but maybe it'll give me a better overall prediction because I've realized that my original estimate wasn't accurate. So I'm not going to go into the math here, and I'm also running low on time, so I'm going to skip over a lot of this. But elastic net regression uses a lot of kind of a little bit of calculus, a little bit of summation type stuff going on. We have different regression calculations we can use. We have different parameters we can use based off of distance calculations between where we're projecting something, what we're optimizing for. And we just try to come up with this overall elastic net regression equation, which combines multiple analysis techniques. And we have these alpha parameters here and these lambda parameters here that we're going to try to optimize for. And we're going to run this over and over again with different values of lambda and alpha to see what gives the best overall result. And k-nearest neighbors for regression, this is trying to get a numeric output based off of that k-nearest neighbors concept that I was talking about earlier. So in this case, instead of trying to classify if something is a different breed of dog, we're going to try to calculate something based off of the average of the cluster that we're looking at based off of the k value. So in this case, if my k value is 3, I'm only going to look at the 3 nearest objects to make a cluster out of, and then I'm going to average their values, and I'm going to use that for predicting something. So kind of breeze through that a little bit too fast, but basically you're trying to get a linear model, picking something that's nearby, picking the k value objects near there, averaging out the results, and that can give you a clustered regression result. So I got 10 minutes to talk through evaluation and validation. So whenever we're trying to do all this, we have to look at how we're going to evaluate if things are good or bad. We have regression models, which are getting numeric results. We have classification models, which are getting either a binary result of true or false, member of the group or not a member of the group, or it's giving us a label result of this is a pug versus this is a beagle versus this is a dachshund or whatever. So different evaluation techniques are used. Most of these are applicable to everything, but some of them are very specific to numeric analysis techniques. That said, loss functions are pretty much universal except for cross-entropy loss. This is where we are trying to take like a Boolean value, like we have this is true or false, and we take the calculated probability of the result that we want, and then we subtract them, and the closer to 0 that we get, we know it is better. And this is done across multiple variables, and we then calculate the total loss of a function, and whichever function has the lowest overall loss, we know that it's performing the best. Log loss is how we do it computationally. We use natural logarithms for the exact same thing I just discussed, except now these are a little more computational. They're more human complex, but they're more easy for a machine to help model. And this also leads us into more advanced analysis techniques like hinge loss, which uses much more advanced machine learning algorithms. So it kind of all builds on each other, how you're doing these analysis techniques. Confusion matrix and calculations, this is something that's very familiar to security personnel. You're used to dealing with false negatives, true positives, and whatnot. This is how we classify our alerts. Well, This is also how we classify the results of our classifiers. Our classifier might give us a true positive, it might give us a true negative being, hey, we thought it was not true and it ended up not being true. And that's good. We like that. True positive, of course, is we think that it's true and it actually is true. But sometimes we're wrong, and we can either be a false positive, that meaning we think that it's true but it wasn't, or false negative in that we thought that it was not true and it ended up being true. And this can play in different calculations, such as precision recall, F1 score, kappa score, a couple others. And depending on what we care about, such as we're cybersecurity professionals, so maybe we care more about recall, care more about finding the true values out of everything. And even if we're giving a couple extra false positives, we might optimize for recall over precision just because, hey, I don't really care if I'm giving my SOC analyst more work. I'm going to look for, I want to catch every single possible positive. So we can overfit models, we can underfit models. Overfit means that it follows the data too closely. That means that the model, if you've ever done like an Excel formula and you're trying to approximate like a function with multiple orders and it comes out with something like extremely long in Excel, you might have overfit the model because it's trying to hit too many outliers. If you've underfit a model, then it just isn't an accurate enough model overall. And we have to tune for this based off of making sure that we don't follow the model too tightly, but not too loosely. So for validation, we will reserve a certain amount of our test data for validation. So whenever you get a chunk of test data, some of it's going to be for training, some of it's going to be for validation, some of it's going to be for testing. And that allows you to build your model. So whenever we're doing our validation stage, we're going to often chunk that into maybe 5 different chunks and run those to try to tune our hyperparameters. Hyperparameters are what I've been kind of talking about with like lambda values, K values, alpha values, etc. And those are something we'll tune specifically. We also have a stage where we're tuning the weights of the equation, like I was discussing earlier. That's whenever we're trying to fit our data correctly. So kind of have to make sure you have a plan for training, for validation, for testing, and all this type of stuff. Now, maybe you want to make sure you have representative samples. You might have to stratify your data so that you're making sure that each chunk represents things at the right ratio of true, false, pug versus beagle, whatever. You want to make sure that your input data that you're training on, validating on, is all equal or representative of reality so that you don't get any bias built in through just bad luck of picking the wrong data to train on. And I kind of talked about that just now. So we take our validation data, we split it up into multiple segments, we check it, we try some different hyperparameters, we check it again, keep on repeating until we've used up all of our data, then we pick whatever works best. We can also manually check this by using box and whisker plots, those cool little boxes with like some tails sticking out of the ends. Those are good for checking to kind of visually see how a parameter is doing. So we have some other charts we can use for model tuning, just different analysis mechanisms. And so I kind of promised that I would talk about support vector classifiers a little bit in my abstract. I'm going to try to cover it a little bit. So support vector classifiers are a more advanced machine learning algorithm. And this is where we start getting into having to look at what our results are and then kind of feed it back a little bit. So we might have multiple dimensions of characteristics we're looking at. So maybe we have, 20 different definitions for attributes of a dog. And we can make decision boundaries for each set of parameters, such as what I've shown here, like, is if the muzzle length and tail curl are a certain way, then it's going to be one grouping. If the pugginess and the wugginess is a certain value, then it's going to be some other grouping. Now, this is individual decision boundaries, and if we combine them together, we're going to get a plane, just, geometrically. Now, if we start putting together a lot of different planes, multiple dimensions, we get what we call a hyperplane. And it's kind of a weird term, whatever, it doesn't matter. This is just how we're going to try to mathematically define the multidimensional combination of decision boundaries that describe a given cluster. Now, whenever we take this cluster, there's going to be a certain outlier range. Now, everything is not going to be, a perfect data fit. There's going to be outliers that hit on either the wrong side of the boundary or close to the boundary. Now, what we do is we establish a soft margin to say, well, if as long as it's this close to the boundary, we're still going to say that it is, this one classification. If it actually crosses the boundary, then we have a separated system. And now we might have to either throw that out or we'll have to adjust our hyperplane equation to account for this. Now, these things which are either close to the boundary or over the boundary are our support vectors. What those do is they drive this multidimensional plane and help define this very complex equation. So here's a little visualization of what I'm talking about in just one dimension. We have something that's kind of crossed the boundary, and we're using it as a support vector. And we're also going to call this a slack variable because it has crossed the boundary, but we're still using it as support. Now, we have hyperparameters. In this case, it's called C, which drives how big this margin is. And it, the higher it is, we get more bias in the system. Lower it is, it's more accurate. But now our support vectors are going to be a little bit different of a overall result. So this is just a classification system, one of the more advanced ones. And just to cover it, just so that I'm covered, make sure I cover all the bases. Sometimes you're trying to do multidimensional work with a hyperparameter that has a non-linearly separable attributes. And what that means is that you have stuff that crosses the decision boundary, and you want to try to trick the SVM into still working. We can do linear algebra, a dot product, to project this data into another dimension and then retune our SVM for that higher dimension. And this is called the kernel trick, which is a big part of how SVMs actually are used for working whenever they otherwise wouldn't. And there's like an entire course you can do on that, but I will not go into that. So that is everything I wanted to cover, kind of giving you a basic rundown of everything with machine learning fundamentals, how to tune it, how data is selected, how some validations performed, and then one of the more advanced algorithms used. Hopefully that was useful. Can take a couple of questions if anybody has any, unless it cuts off automatically, I'm not sure. Yes, so in terms of balancing bias, I mean, you're going to have some bias and you're going to have some predictive variance, and you can't remove either. Ultimately, you have to kind of decide, do I prioritize bias? Do I prioritize predictive variance? Which do I want to try to remove? Because as you lower one, the other one just inherently goes up. And then you try to minimize it, of course, through hyperparameter tuning. But again, as you change one thing, you're going to lose something else. So it's really about optimizing for what your goal is. Monty, did that kind of answer your question? I don't really know if it was a good answer, but yes. So whenever you're running a model, you'll loop it with a set of hyperparameters. So I didn't really talk about it, but there's something called grid tuning or grid searching. And that's where you take all your hyperparameters and you kind of make a grid out of them. So if you have a lambda and alpha, and you have, say, 30 things you want to check for lambda, 30 things you want to check for alpha, you put them in a grid together and you get this big array of, 30 by 30. And then you run the model fit and then do the validation steps and get your loss equations and all those types of things out as the output. And then you compare for each grid search run, what has the ideal characteristics as the output. And by the way, that can be very computationally expensive. It's why grad students are sitting there like, oh yeah, I'm still running my model. It's been 2 hours, still running it. Chris, in terms of math, most of this runs off of linear algebra. Some calculus should be expected. Generally, as long as you have Calc 1, 2, and linear algebra, you probably can do most of this. You probably should at least understand multivariate calculus, just because you're going to be dealing with summations in multidimensional space, and that tends to be a Calculus 3 topic. But, it just really depends on how hard you're going on the math. Like if you're calculating stuff by hand and validating it by hand, you need to know it. But otherwise, you're kind of just looking at, I didn't show many equations on this, but most of them are just basic Calc 1 and 2 type stuff for the most part. In terms of recommendation of courses, honestly, I just kind of ML AI type courses going through college. So there is knowledge engineering, which is some of the older expert system type stuff, learning like the Lisp programming language, LISP. That's an older school method that deals a lot more with symbolic type stuff and expert system type stuff. And then pretty much everything I've been doing is in Python. So that's very useful language to learn. And then understanding data structures naturally is pretty important because these things have to be pretty heavily optimized, because you don't want to run like a 5-hour long optimization and you're doing it very inefficiently. So that's why having a good background in data structures can help you. Just because I don't think I've had to do any differential equations for anything that I've discussed so far. I did actually have to take what would have been differential equations 3 for my master's degree. And that was in exploring multiple input, multiple output real world systems. And that can be very complicated. So modeling them mathematically did require us to do differential equations. But for doing the machine learning portion, I don't think you would need to know it, but I'm sure somebody could correct me on that. I haven't had to use differential equations in a machine learning class so far, but I have in mathematical modeling classes. Any other questions I missed? I don't think I did. I'm trying to watch chat. Alrighty. Well, thanks everybody for coming. Hope everybody learned something. Have a good one. Yes, Tyler Hardy on LinkedIn. Thanks. Have a good one, everybody.